solvability of this equation is really solvability of this linear congruence equation, modulus p minus 1. That's what's happening to the exponent. From there, we can calculate the number of solutions. We can describe all the solutions with some additional information in this exponent form. Right? So that was the it's been a while that you took the differential equation a long time ago. This particular solution in homogeneous may not make sense, but this one you probably remember. So what I'm doing right now is kind of throwing additional structure to the three statement. I'm about to draw you a nice picture. Linear algebra. This is Rn, right? What is this Rn called? The space of column vectors with n entries, right? And there's a linear transformation given by matrix going to what size of the vector? Arbitrary size, whatever it is, m, right? Space of column vector with m entries. There's a matrix, right? This matrix has something called a kernel. Remember a kernel of m? Something that becomes 0, something that dies under this thing. And there's a rank theorem. There's nice theorem, things like that. So solving this equation, system of equation, and here I'm looking for solution. This is correspond to I have a matrix. I'm looking for this n size column vector. My output is let's say m size column vector. This is given as system of linear equation. This is a fundamental problem the elementary linear algebra begins with. System of linear equation, m equation here, and n variables. This is very algebraic, and you start with it. At the end of the linear algebra, they pull out this nice function picture and tells you, okay, if I have, I'm going to write down this one is a w here, w0. If I have one solution here, x0, particular solution, and all the solution is coming from adding the kernel, whatever is inside the kernel. This is analogous to particular solution in differential equation and homogeneous solution added to that. That's why they brought up this linear structure in the context of a differential equation and things like that. So I usually geometrically view like this, and here is the kernel. It's a sheet or hyperplane in three-dimensional space. Think about one plane in three-dimensional space that passes through 0, 0, 0. Can you imagine that? One infinite plane, right? That's usually the shape of the kernel in that structure. Yeah? If I have one solution here, x0, where's all the other solutions? What you do is that you shift that kernel to right there. Kernel is down there passing through 0, 0, 0, right? And you shift it parallel so that it passes through one solution you found, x0. Then the plane is parallel shifted and passing through one that you found, x0. All the other vectors here happen to be the older solutions, and that's it. So I call is a shifting phenomenon. You have a kernel, you shifted one solution that tells you everything, right? So it's a shifting. So here's our situation. All right, we have FP here, right? FP star. What is the horizontal map in the commutative diagram? Log 7. Is that right? Log 7. And here's the z mod p minus 1, right? Let me use just log g and switch back to log g. What is the vertical map we're looking at here? X to the n kind of map, x to 21. What about this map here? N times y. It may switch to different variable y, but it's correct. N times y. And this one is a z mod p minus 1, right? And what is this horizontal map? Down there. It's a log g again, right? Okay, this is a familiar one. So we're focusing on this part in here. Think about it as if it is a vector map. We have one vector space and going down to, there is something dies in that process, right? Something dies, just like the linear algebra here. You hit in the matrix, that becomes a 0, that's the kernel. So that will be the kernel of that map down here, right? We call this one map F, right? So it's appropriate to say the kernel of F. whatever that dies here, dying means becoming 1. I was here the 213 raised to nth power, it became 1, and that's where we might die. All right? So what is that goes down to 0 here? It turns out, you know what that is? It's generated by anything that raised to nth power here that dies. That's what that is, right? This is exactly that zeta that we calculated. Right? What was the property of the zeta? Remember? Any element of order n or what? Not n, d, right? D. So that's the order d element. That's the description. So that's the picture that's analogous to that. Right? This much of the element that dies there. So how many elements are there in the kernel of M here in this case? In the column vector space, of course, there's infinite points, but we have only finitely many elements. This is a kernel in there, right? So how many elements are in there? Bracket zeta, where zeta, so order is d. Right, 7 here. So d elements, exactly. Inside of the d elements. So in the finite case, only d elements in there, right? D elements. So they're all going to w. How many elements are here? If you shifted, number of elements doesn't change. You shifted it, right? So there's a d elements right there. So there is this d elements. How many elements are here? D element. They're all going down to 1 element there. That's the situation. This map, x to the n, take the bunch of d elements there and collapse it down to 1 element. What are these d elements described here? What are those? Those are exactly this thing. One particular element multiplied by the power of the zeta. Those are the fiber. That's the geometric term. Fiber. D elements maps down to the d elements. So there's a group of another d elements there, right? They map down to something different, right? Something different. So this is nice structure analogous to linear algebra. It's called d to 1 map. Does that make sense? D things go down to 1. Not 1 to 1, d to 1 map, right? So these are the geometric terms. That kind of helps you to understand this formula that we have right here. Right here. Okay? Commutative diagram branched out a little bit further with this one. All right? There's something else kicking in here. What was that here? A kernel of? I think we used h here, right? F over here, h there. So this is kernel of h. This will be tricky. What is that going to be generated by? Right? It's an element inside the p minus 1, d mod p minus 1. That looks like fantastic homework problem to figure it out. So there's a zeta. It's related to the zeta. An order formula. If you look at the order formula, it tells you where is this. Here, we discussed it here. What is that exactly that generate the zeta in terms of g, right? So if you look at this one, it tells you, it's just a matter of hitting with the log map, right? We know zeta in terms of g, so what is that going to be over there in the second column? You just hit it with a log map, right? Log map. So here, zeta there, we know in terms of g to the something, and that something is going down there, right? So we have that structure, and underneath it, we still have this log map restricted down to still isomorphism, right? This thing grows as you, go in higher and higher mathematics. There's a snake lemma and all kinds of lemma is to complete this diagram. These arrows are going crazy, all right? But that's the picture. I think it's, in my opinion, it's better than memorizing these 3 sentences. Maybe that's the way I look at the subject. But it's a nice picture to have in mind. The criterion and more beyond Euler criterion. All right. We are in quadratic congruence, and I'm not just talking about x to square equals a. I'm talking about all the higher power here, right? So this is the application is. Who remembers Euler's criterion? Right. So I'm going to write down x squared is congruent to a mod p. This is happening in FP, right? FP, and especially in star. And this is if and only if there is some some power conditions, right? This is solvable. Maybe that was solvable, right? Remember that part? X squared equals a is solvable. And what was the condition? It was about, right, a to the p minus 1 over 2, right? And this is equal to what number? It's 1 if it is solvable, and negative 1 if not solvable, right? So that's one statement. And second statement is that a raised to p minus 1 is becoming negative 1 if and only if x squared is what is it? Not solvable, right? That's the Euler's criterion. So one of the Sage homework problem will be, is this really effective? Then I have p minus 1 element. I'm going to square it. I have a list, right? And I'm just going to figure out if that guy appeared in the list. All right? There are two different ways to determine using computer power that given number h, a is square or not. All right? So here's one method you're going to do. You're going to square everything. 1 to p minus 1, right? In Sage, you square it, and you get 1, right? What happens if you square p minus 1? Does anybody know the answer? It's a negative 1. So if you square it, it becomes positive 1, right? So there's a 2, it becomes 4, right? Eventually it becomes weird as you mod out by p, right? So you have 1 and 1 appeared again, 2 and there's, so what is this map? 2 to 1 map? Does that make sense? Like d to 1 map here is x squared is a 2 to 1 map because 2 completely divides p minus 1. GCD in this case is 2. So it's a 2 to 1 map. Two things here and there map down to one thing, right? And 2 and whatever p minus 2 map down to one thing. So you look at it here, hey, there's 3 missing right there, right? Therefore, 3 is not a square. Is that the correct conclusion? No. 3 might appear somewhere down there. It's all out of order. So maybe nice algorithm is that you sort it first, right? The command is a sorted. You take the list and hit it with a sorted, and then Sage is going to sort it. Then you find your number A, whatever, and if it's skipped, then you know it's never going to appear because it's sorted, right? And concluded it's not a square. It did not appear in my entire list there, right? So that's one way to conclude given number A is a square or not, right? But Euler says, all right, here's a different method. Why don't you take that number and raise to this high power? If that becomes 1, it's a square. If it is not, it's not a square, right? So that's the, so it's going to be statistics. That you're going to run through your algorithm of all that thing and kind of average the time and see if that really wins or not. If I happen to choose A quite close to that range, maybe your algorithm happened to find it, so the accidental thing gets ruled out. You have to try lots of numbers. So I'm going to give you a sample and see if your time-wise you compare with these two things and see if that really wins. Is that who can argue right now which one is a better argument? I mean, which one is a faster algorithm? This takes a lot of powering, right? Although it's power mod is doing a good job, and versus you have to actually square the p minus 1 elements in there, right? So that's why I'm doing this. You've got to have a feeling that is there one method is particularly better, something like that. All right. Next part is I'm going to focus on a non-trivial part right now, and one direction is trivial and non-trivial. So I think if you prove this one, the other part's easier to prove it. So we're going to focus on one thing. If it's not solvable, that means it's not 1, and what is the other possibility? The 1, you have to conclude it is negative 1. That part's easy. So we're going to focus on that part. And if you assume x squared equals a, it's solvable. That part's easy, actually. If it is solvable, then showing that this is 1 is also easy. So assuming that we have this situation, which is really what we're relying on for that algorithm that we're going to do with the Sage, this one implies x squared is a bit non-trivial. So that's what we're going to focus on. So proof of a raised to p minus 1 over 2 equals 1 implies x squared equals a solvable, right? That's what we prove. But let me write it like this. X to the a raised to p minus 1 equals 1 means x to the, why don't I write this one? No, I'm going to leave it as x to the p minus 1 over 2 equals 1 is solvable. Who can explain what just happened? A to the p minus 1 over 2 equals 1 implies that x to the p minus 1 over 2 equals 1 is solvable. So there's some profound reasoning or very trivial reasoning. What is the solution if it is solvable? You're right, Beth. A is the solution, right? You stick it in A. Obviously, it's solvable, right? So let's think about that first item of the theorem. What is that saying? Number one item. There are three items in the theorem I introduced today. What is number one item? If it is solvable, what linear congruence is solvable? N, what is N here? N is this guy, right? So that N, which comes down to p minus 1 over 2, times y is congruent to k, right? Good. What is k in this case if the right-hand side is not a, but 1? What is the log of 1? 0, right? Does that make sense? If you go back to the x to the n equals a condition in here, what was k that appeared here is a log value right there. Log value is appearing in the exponent level. So down here, so what is the right-hand side? Again, log value of 1? Log of 1 is 0. Modulus, which one? P minus 1, right? It's exponent level, p minus 1. So this x to the n equals 1, solvability is exactly the same as this linear congruence. So what is the next part we do? To solve this one. GCD of this coefficient and the modulus, right? What is the GCD of these two things? P minus 1 over 2 completely divides p minus 1, right? So GCD is p minus 1. So we're going to divide everything. This number and that number and that number divided by GCD, right? So what do we have here? Divide by that and you just y, right? 0, whatever is divided by is a 0. But what's the modulus? 2. Only 2 is left, right? P minus divided by 2, divide it out, what's left is just a 2. That makes it p is an odd prime here, right? Okay. So what's the conclusion here? Y is even number, right? So y is even number. So can we write down y is an even number like that, 2k. Is that okay? Any question? Y is an even number, 2k. But we were originally interested about this solution of x in there. X, right? If y is 2k, and what is x? If you think about the commutative diagram again, here x is going down to that number y under log map, right? How do you go back if you have y? Exponential map, right? So what is a g to the 2k? It's happened to become, right? So there, solvability there. So we conclude that, okay, if y is 2k, x value that we're looking at there, it must be 2k. G to the 2k. Is that right? Whatever that x was is always g to the 2k. So if x was, that implies that if x was this number a, that must be in this form g to the 2k. For some k that depends on a, right? Right? Does that make sense? All right. Again, if we have a raised to p minus 1 over 2 equals 1, then it happened to be the solution of x to these large power equals 1. Under the theorem, we conclude that x must be, that a must be in this form, g to the 2k. Right? What is that we wanted to conclude here in the original theorem? A is a square of something, right? Do you think you can write a as a square of something? G to the k squared, right? We pulled out 2 out of the exponent level. Therefore, it's a square, right? Isn't that neat? So that's why it's back and forth is true. All right. So going back here, So we proved that this one implies that, and that one implies this one. If you stick it in there, it's relative.